Alright, forging onward into chapter 17. Things should be going, pretty well by now, right? We have got all of this under control. We understand the general mechanism. We know our new carbonyl electrophile, that H- reagents and organometallics add happily to either reduce the carbonyl or make a new carbon-carbon bond with an alcohol, or in the case of the Wittig, wow, a new way to make an alkene. So why don't we just call it a day and stop here? Well, because we still have some more stuff that's really important to cover, and that's the realm of conjugate addition. So conjugate addition comes into play, as you might expect, whenever we have a conjugated carbonyl, as in this cyclopentenone. So looking at that cyclopentenone, we know that, of course, there's a reason why, for example, the IR stretch for a conjugated ketone is lowered, more like 1680 instead of 1700 or 1710. Why? Because of this resonance contributor that shows the single bond character between the C and the O. What does that have to do with this topic? Well, what it's showing you is that, I have a carbon electrophile right there. And of course, that's the carbon electrophile we've seen all along in this chapter. But wait, there's more. Because of course, there's that resonance contributor too. And therein lies the problem? Well, it's not a problem, it's just a reality. We have a carbon electrophile at that point as well. So, when we have a conjugated carbonyl, what do we have? We have two different electrophilic carbons. Two different places where our nucleophile could attack. The place, if say the nucleophile is H- and it attacks at the normal carbonyl, the one we've seen all along, just attacks right at the base of the CO double bond, well, that's 1,2 addition, and of course we get the alcohol. The alkene is left alone. But it's certainly possible that your nucleophile could attack at the red position as well. In which case, again, if it's an H-, H- attacks there, your alkene disappears. Basically, what you've done is put your H- there, and in workup you put an H+ there. You've got 1,4 addition. The ketone remains untouched. The alkene disappears. This obviously leads to issues of selectivity and control. We want to be able to control whether we get 1,2 or 1,4 addition, or we at least want to be able to predict it. So let's first look at the mechanism for 1,4 addition, and it's actually pretty straightforward. Basically, my nucleophile attacks at that 4 position, kicks that pair of pi electrons up to make a charged intermediate that happens to be an enolate. So that's a resonance delocalized intermediate, of course, because of that resonance contributor. And if in the workup I pick up a proton, then you get your 1,4 product. So there's your mechanism. Now, what's the story? When do we get 1,2? When do we get 1,4? Well, more than anything else, it really depends on the nucleophile. So it's not really something we can control. It's just something we can predict. And that's what we're going to learn about in the next few slides. It really boils down to two things. Does my nucleophile add reversibly or irreversibly? And as a result, is the reaction under kinetic or thermodynamic control? I am going to try and explain this by using the concepts of hard and soft acids and base. This is an old theory. Basically, it was developed for inorganic chemistry, but it's really pretty helpful in explaining 1,2 versus 1,4. So, hard versus soft. When I look at my two possible electrophiles in my conjugated species, that carbon versus that carbon, I'm going to characterize one of them as hard and one of them as soft. So how am I going to do this? Well, the hard electrophile, this guy right here, is hard because that positive charge is concentrated on that carbon. It's right next to the negative charge on the oxygen. That's a very highly developed positive charge. So I think of that as kind of an intense positive right there at that carbon. Whereas for this particular positive charge, you know, it's delocalized, right? We can draw a resonance contributor that shows that it's delocalized and way over here. So since it's further away from the O-, it's not nearly as intensely concentrated. Now this is probably going to sound pretty hand-waving, but it works. Okay? So when all is said and done, the 1,2 position is my hard electrophile, and the 1,4 position is my soft electrophile. So what does this mean? Well, it means that a hard nucleophile is going to react at the 1,2 position. Hard reacts with hard, soft reacts with soft. So, all right, let's try and look at this in a little bit more detail. If this is going to help us at all, we need to understand what makes a nucleophile hard or soft. Kind of alluded to it already. The hard electrophile has this hard concentration of charge. The soft electrophile is delocalized and further away from any really full charge. So we're going to apply those same things to our nucleophiles. So a soft nucleophile is one, for example, that is delocalized. An enolate would be a great example of a soft nucleophile because the charge is delocalized throughout the CO system. Okay, that's a good example, but what about these guys? Well, those guys would all be considered soft nucleophiles because the charge is on a little bit more electronegative atom, say more so than a C- or a C- of an organolithium. Okay, so that means they're a little less intense, right? They're more stable because they're on a more electronegative atom. That makes them soft nucleophiles. All right, so as a result, these soft nucleophiles add reversibly, and that's important to remember. They add reversibly, and because they can be kicked back out again, overall, that means the 1,4 addition is the thermodynamic reaction. So how can we tie all of this together? Well, let's look at an example first. If I have a Grignard, knowing what I know about Grignards, I would consider that a very hard nucleophile. After all, we're sort of thinking about this as this guy. That's a very, very, very strong base, so we would expect it to go 1,2, and in fact it does. But a thiol, like this methane thiol, that's really soft. This is not only a big electronegative, soft, diffuse atom, it's not even charged. So this guy is unquestionably going to go 1,4. Completely different products. One gives me an alcohol, one gives me the ketone that has lost the alkene. All right, so how do you tie it all together? Well, this figure out of your textbook actually does tie it all together. But as you can see, it's kind of a nightmare. So we're going to go through the key points and then re-examine it. So the key points from figure 1715 are 1,2 addition is fast. It's faster than anything else, especially when you're using a hard nucleophile. Why? Because hard nucleophiles have a hard charge, and we know where the hard positive is. We've got a hard negative. They're going to be attracted to each other and lickety-split bond. All right, so kinetically speaking, 1,2 addition is going to go faster when you're using a hard nucleophile. Okay, I can buy that. Now, when you do the addition, you get a charged intermediate. The charged intermediate for 1,2 addition, which is this guy right here, is not very stable as compared to this guy. Why? Well, in this guy, of course, the anion is delocalized. All right, so the 1,4 intermediate is more stable. The 1,2 intermediate is less stable, and that's going to make a big difference. All right. Furthermore, when a hard nucleophile reacts with a hard electrophile, thermodynamically speaking, you're making a very strong bond, and that makes it irreversible. So once a Grignard or organolithium reacts with a CO double bond at the 1,2 position, it sticks. There's nothing reversible about that. Whereas, so let's just make this clear, that reverse reaction here, where maybe this would come back out and kick that out, you know that's not going to happen. That is very disfavored. Terrible leaving group. Don't go there. Okay, and then the last key point is that when you make the 1,2 addition product, it's not the most stable. Why? Because in 1,4 you are making a rock. The CO double bond is a super strong bond. All right, you lose the CO double bond in 1,2 addition. You retain it in 1,4 addition. All right, let's pull all these together. Here it is again. So just to reiterate these key points, looking right here, we can see that the blue addition of my nucleophile to my hard 1,2 electrophile goes fast, goes much more quickly, because, get some different colors here, right here, this is a shorter delta G double dagger. It's more quick because of the stronger attraction between the more intense charges. All right, fine. All right, what else? So that shows that 1,2 is kinetic. All right, now we said that the kinetic product from 1,2 addition, right here, is less stable. Why? Because we lost the nice, strong CO double bond. So this illustrates the differences between the kinetic and the thermodynamic product. It's all because of the stability of the CO double bond. And then finally, the other key point, as I said, was that the energy levels of the two intermediates are different. All right, that when you look at the 1,4 intermediate, it is more stable because you have a delocalized negative charge, whereas for the 1,2, it's not as stable because it can't be delocalized. Oof, that's a mouthful and a headful. Basically, it boils down to hard nucleophiles are 1,2 nucleophiles that add irreversibly and quickly to give you the kinetic product, whereas soft nucleophiles would add, let's change this to red, My soft nucleophile would add here. So what we're showing right here. It doesn't go as quickly, but it leads to a more stable intermediate and ultimately a more stable product. So as long as I've got reversibility, boom, I've got 1,4. Oh, holy cow. So everything's great. We understand that fully. It takes a long while to sink in, granted. And now we throw in the wrench. What do we make of this new nucleophile, the dialkyl cuprate? Well, here is a perfectly good conjugated ketone. And if I add a Grignard, as expected, I would get 1,2. And if I add an organolithium, as expected, I get 1,2. And if I add a CH3Cu, which happens to have 2 methyl groups on it, and this whole thing is negatively charged because it's copper plus 1, so it means there's a lithium plus 1 counterion. Well, you know, surely that would add 1,2, and it does not. So that's the wrench. We have an organometallic now that adds 1,4, and it's the cuprate. Alright, so we have 3 different kinds of organometallic reagents now. Grignards, organolithiums, and cuprates, but cuprates are different. They are soft. How can you remember this? Well, one way I like to remember it is copper is a transition metal. It's a big fluffy teddy bear of a metal, if you will. That's how you can think of it as a soft nucleophile. I gotta tell you, it's not that simple. The mechanism is not well understood, but the bottom line is, if you want to add a carbon 1,4, it's going to have to be either an enolate, as we will see later, because an enolate is a soft nucleophile, or an organocuprate. Whew! Alright, let's quickly summarize what we've done so far. We know that hydrides are hard reducing agents. They reduce carbonyls to alcohols. Organolithiums, Grignard reagents, very hard organometallics. They add 1 to the carbonyls quickly and stick. They're irreversible, 1,2 all the way. Turns out the Wittig is also a hard nucleophile, and it gives the alkene in the place of the CO. And then there's a bunch of soft nucleophiles. So it turns out nitrile is a soft nucleophile, only because of the electronegative nitrogen being so nearby. Alkoxides, enolates, and now cuprates add to the soft carbon, the beta carbon of a conjugated system, and give predominantly the 1,4 product. Alright, so bottom line is we've just gotten out of our cross out the spectator ion and ignore it phase, because the counter ion actually does make a big difference, especially when it comes into the realm of organometallic chemistry. Alright, so that's it for this mini lecture. We'll do some examples later, and we're getting close to the end, so hang in there. You will survive.